So, hey everybody, I'm John Handler, Senior Principal Solutions Architect for AWS. I work with tons and tons of customers working on vector workloads, and today I hope I can bring you some additional tips and tricks and ways that you can optimize your storage and get deployed right for OpenSearch for your vector workloads. Won't be a huge new piece of news to anybody, but I thought I'd get us situated by starting with, well, okay, so what is OpenSearch about? Really, I have a person somewhere, I have a bunch of knowledge somewhere, and OpenSearch is mediating between the person and their information goals and the big set of knowledge that is stored in OpenSearch. And as everybody probably knows, lexical search has been, until the last 5 or so years, the main way that that happened. In this case, if I search for a gaming headset with microphone, you can see I have 2 example products there. Clearly, there are more matches in the bottom product, but these are both retrieved because they match the words, right? And so when the embedding models started coming out, and again, by way of being situated, embedding models take text and generate vectors. And just because everybody always says vectors but don't show vectors, here's an example, a small piece of a 1500 dimension vector. That's what it looks like, dense vector. It's a bunch of numbers in a big array. And OpenSearch's job, again, as a mediator between somebody who has an information goal and some big store of knowledge, is to be able to match that and bring back relevant results. We talk about a multi-dimensional space. This is a projection of about 20,000 points. All of them are sourced from vectors like that one. And this is kind of, conceptually, we've projected it down onto 2 dimensions so you can see it. But what you can see is we learn correlations, backpropagation, and the embedding models learn the correlations between the text input, placing them in this space in such a way that we can retrieve them based on vector matching. So what is semantic search is the means of matching vectors. We create a vector embedding for the query. If you can't see it, there's a much larger dot kind of right in the center there. And the core idea is, okay, well, we'll retrieve based on distance within this big space. If it's really close, then we'll say that's similar, we should retrieve that one. If it's far away, we'll say, okay, that's not similar, we should not retrieve that one, right? That's the core of what OpenSearch is trying to accomplish when we're doing semantic search and vector matching. So within OpenSearch, you have many, many, many different ways of accomplishing that, and we'll touch on most of them. But apart from this straight knowledge retrieval, OpenSearch has, as a vector database, has several core use cases. So first of those is AI-powered search. Store vectors, match vector queries, use exact matching or approximate matching, and be able to filter and run hybrid queries to bring information directly back through an application. The second of those is knowledge base. We talk about retrieval augmented generation. We talk about conversational search. OpenSearch plays a role to provide accurate information so that the application that is chatting with the user, or the user that's chatting with the application, gets the right answers, and the LLM that's summarizing on the right is not sending out bogus information. With agentic search, then, we also see within OpenSearch there's an agent framework that provides the ability to contact an LLM to do reasoning and planning and retrieval on top of, amongst other data sources, OpenSearch, and bring that data back. So these are kind of all of the places that you might employ vectors. So the topic is about scaling and optimization, right? We kind of now know these are the core workloads that you might be looking at when you're dealing with vectors in OpenSearch. The drivers in terms of scale, like how do vector workloads distribute across the resources that you deploy in an OpenSearch cluster? First of those is CPU. CPU obviously is about request processing. When you send a request to OpenSearch, it's going to be distributed across shards, and each of those shards will process it. You want to really be careful to optimize your shard and CPU ratios so that you have enough CPU to drive the workload. And with vector workloads specifically, the background tasks can actually be a little bit heavier weight than straight up text workloads. The vector workloads are, as we'll see, some of the approximate methods have indexing time and merge time work that they have to do that can drive more CPU. We also have our Java heap. So during indexing, the workload will drive the heap. As well, during search, especially processing transient structures like aggregations, we have to worry about heap. Not so much for vectors. Memory is where vectors actually come into play quite a bit. And so Lucene uses off-heap memory to speed searches. Vectors also reside in off-heap memory. That'll come up. And there are parameters within OpenSearch where you can set the ratio of heap to off-heap, where you should lean towards off-heap if you're running vector workloads. Last of those is storage. Index data sits on disk, and your storage affects your search and indexing throughput, like SSDs provide you faster search throughput, faster indexing throughput. Useful for search use cases, less so for logs use cases. So these are our core kind of resources that we're going to be considering. The index is the destination for the data. So when you use OpenSearch, if you didn't know, you create an index. That index is going to hold all of the search documents that you send in. They're kind of tenants of a cluster. Within each index, then, you have a set of Lucene structures called segments. Each of those segments is a portion of an index, and queries have to run across all of them. So you send your documents to an index. Each index then is composed of shards. Shards are the workers in the cluster. They are sub-elements of an index. Each contains a discrete set of documents. And then OpenSearch maps shards to the nodes that are in the cluster, the data nodes, so that the data nodes do the processing. For request processing, the requests will reference some index. They'll land on some node. That node will serve as a coordinator. Within OpenSearch, you have the ability to specify a particular node acts only as a coordinator, or your data nodes will act as coordinators for a request. The coordinator's job is to read the request, parse it, split it into the sub-requests that need to go to the shards for that request, and then distribute those sub-requests, receive the results, aggregate, and send back out. So if I'm looking at a search query, the coordinator is going to say, okay, this index has shards on these 7 nodes. It'll create 7 internal queries, send those queries to nodes that have those 7 shards on them, and then each of those shards will reply back with a shard-level response that the coordinator will aggregate all of those shard-level responses to send back out as the query response. Below this kind of layer, each node actually has a number of different queues. And each of those queues corresponds to some kind of work that that node is going to do. So there are write queues, there are search queues, there are segment merge queues, there are, I don't remember, it's on the order of tens of queues. When a request comes in, it gets queued, and it is then sent to the node that has the data, the shard for that data. On that data node, for the sub-request, it's also queued, and then dequeued, and then goes to the CPUs and the threads, and those are the things that ultimately access disk and storage RAM, whether it's heap or off heap, to serve that request. So that's how request processing goes. So let's talk about how the data is actually stored. So if I have a document coming in, and this document has some attributes on it, metadata attributes, it also has a vector. It's going to go to the shard. The shard is then going to, all my pictures didn't come up. The shard is then going to take the metadata and index it into a Lucene index. It's going to take the vector data and index it into also the Lucene index in this case, right? So the structures that it uses are, first of all, a posting list for metadata. Posting list takes the values that a particular field can have and creates a list of all of the documents that contain those values. It stores the source, so the source document, unless you disable it, the source is on there as well. There's also something called doc values, which is the forward map from a document to the values that are in that document. Those are used for some kinds of tasks. A bunch of other files, there's 30 or 40 Lucene files. On the vector side, we're storing source, and then we're storing vectors also in doc values. And we also have, if you're using approximate matching, we have ANN, approximate nearest neighbor data that's stored there as well. For approximate methods, we also put ANN data into RAM itself. So I don't want to dig too much into this, but the structure of how things lay out within a particular data node, you can see we have some caches that are at a field level, at a query level, at a request level, and we also have separately vector caching. We have, for each shard, we have an index and we have a vector native library. So as the data lays out, we have these separation of metadata and vector data. All right, so that was more by the way of background, just to understand sort of the structures and what's there. The core thing we'll talk about is plan for a workload with 125 million products. Each of them has about 2K of metadata, and we want to support semantic search with vectors with 1,536 dimensions. So let's talk about the different paths of the vector indexing. The metadata is going to be converted into index. As we said, there's posting lists, and there's source, and there's all of this other stuff. As a rough guesstimate, the per document size, index size, is the metadata size with about 10% inflation. There's a lot of parameters you can use to affect that. There are different compression methods that OpenSearch provides. Modern OpenSearch, we see it being lower than that, 70, 80% from source to index. But use 10% inflation as a very conservative guide to figure out how much storage you're going to need. When you're figuring it, you also need to include overhead, because OpenSearch is going to degrade the service of the node when it starts to fill up the storage. So beyond, there are several watermarks. Beyond 15% free space, it will stop allocating shards. Beyond 90%, beyond 90%, it will start to move shards, and beyond, at 100%, it will stop accepting requests, right? So you always need at least 15% overhead, and we recommend 25% overhead in terms of free space. So when we're calculating the size of the index we're going to create, we add in that 25% as well. So on disk, document count times metadata size times 1.35. That's what the metadata will represent. So 125 million documents with 2K of metadata comes out to be about 345 gigabyte for that piece. So now looking at the vectors, we have the dimensions for the source vectors themselves. We have the dimensions, the number of bytes per dimension, and then we actually need 2 because we're storing it in source and doc values, okay? So we can figure that out, document count times the per document size times 1.25 to leave overhead, and 125 million docs with 1536 dimensions with full precision vectors, and for exact search, we're ending up with something like 3 terabytes. So you can see how actually vectors drive a lot of cost in terms of the amount of storage that they consume, just the raw storage. I had actually, the example earlier was for 2 vectors per document. Ignore the last line there. Sorry? I'm sorry, I didn't hear.
Where's the document itself?
The document itself is only in source if you save it in source.
Okay, so you assume you're not saving the source document.
No, you are. So for vector data, you have this factor of 2, vector dimensions times bytes per document times 2, because you have source and doc values.
Okay, so
yeah. Yep. All right. All of that assumes that you're just storing vectors, and your query is going to use exact matching to brute force match against what you have, the vector index. It doesn't scale. So exact is great if you can highly filter your vector count, so you're only doing thousands, maybe tens of thousands. The latency goes linear with the number of documents, number of vectors. So approximate algorithms enable you to actually reduce the latency, and also you reduce the accuracy. And so you end up with not as good matching, but good enough matching at a much lower kind of cost. So there are 2 methods that OpenSearch supports. It supports something called HNSW, that's Hidden Navigable Small World. The idea here is, at indexing time, you create a set of graphs for neighboring points. And you have different granularities. So you construct a graph at a high coarseness level, and then you traverse that graph to get close. You drop down to a finer grain. You traverse that graph to get close. You traverse to as close as you can, and eventually, at the lowest layer, you just pick the nearest points there. Key parameter here is the number of edges in terms of storage and in terms of efficiency. So this is parameterized. You can set, the default is 16 edges per node. And all of the graph construction, all of that's automatic. As I said, that's at indexing time to do that. So in addition to the source and doc values that we already talked about, the 3 terabytes, you're now going to create a bunch of graphs, and you have to store those graphs, and those graphs are going to be in RAM. The formula for how much memory they're going to take is 1.1 is a little bit of a buffer, 4 times dimensions, plus 8 times the number of edges, times the number of vectors. Make sense? You're taking 4 bytes per dimension, and you have 2 edges per node in the graph, so that's 8 bytes times the number of edges, times the number of vectors to get the total storage for that vector data set. If we fill in our numbers here, 1.1 times 4 times 1536 dimensions, plus 8 bytes times 16 edges, times 125 million vectors, that's going to give us 862 gigabytes of graph data. So for the storage, we also want to add that 25% overhead. So we take 1.25 times the RAM, giving us another 1.08 terabytes of storage. Yeah? Not yet. Okay, second approximate method is called inverted file. Yes? Yes.
So where does the 4 come from? Is like the integers?
The 4 bytes is for 4-byte floating point numbers.
Oh, I see. How do we report the storage of edges at degrees m?
So m is the number of edges per node.
And 8 would be the
2 pointers. Yeah. Make sense? Yeah, because it's a 2-way graph.
Right, and each pointer is a
32-bit pointer, yeah. Okay, let's talk about approximate method number 2, inverted file. The idea with inverted file is we use k-means clustering. to find centroids of related points. We then put those centroids into some number of buckets that's configurable, and when we do a search, we find a close centroid, and then we can search within that bucket. The key parameter here is nList, which is the number of buckets. Okay? Again, the idea is reduce the search space by finding some close centroid and then just search it right around that. And these centroids are representative of their cluster of points, right? This does require training, so there's a training step for using IVF where you take about 10% of your data and that's how you figure out the centroids. But it's an API call, you just call train. So in terms of the RAM here, we have, again, 1.1 for a little bit of fluff, 4 bytes times the number of dimensions times, what is n again? Shoot, I'm standing on stage, I'm losing my brain. So let me just do it in my head, plus 4 bytes per entry into the list. Oh, n is the number of vectors. I'm being dumb because I'm talking to you. So 4 times the number of list, the number of buckets times the number of dimensions, and that gives you 844 gigabytes. My commentator, we now have to double everything because this whole deployment is for one shard. And normally when you run OpenSearch, you're going to run with at least one replica shard to improve the resiliency. So we have to double everything for a replica. So where we are up to this point, we have 125 million vectors, 1,536 dimensions with 2K of metadata each. If you're going to do exact matching, you don't have any of the approximate stuff, then we need 2 times the 3.52 terabytes. That gives me about 7 terabytes of storage that I need to deploy to hold that. If I use HNSW, then I have 345 gig of metadata, 3.07 of vector data, and 862 of graphs. That makes, with the doubling for the replica, I need 8.5 terabytes. I also need 862 gigabytes of RAM to hold it. If I'm using IVF, again, I won't read the numbers at you. I need 8.2 terabytes of storage and 844 gigabytes of RAM. To this point, it feels like that's a lot, right? Now, 125 million vectors is a lot of vectors, and 1,536 dimensions is a lot of dimensions. But these are the resource needs just in terms of storage if you're going to use these different methodologies. You might wonder, can we do better? Well, yes, we can. So let's talk about that. First thing I want to talk about is derived source. So derived source is a feature that was released in 3.0. You can enable it when you create your index. You say KNN derived source enabled true. What OpenSearch then does is instead of storing data in the source field and instead of storing data in doc values, it creates a separate file called the .vec file that has all of the original precision vectors. It then can recreate source and doc values from the .vec file. And there's a bunch of writing. It's as performant as storing those two things separately. And it provides you with a means of greatly reducing your storage, right? Because now instead of 2 copies, you have only 1 copy of your vector, your original precision vector data. So on disk, you have the .vec file and the ANN data, whether it's graphs or buckets. And in RAM, you still have the ANN data. So for exact, that brings us down to about 3.74 terabytes. For HNSW, that brings us down to about 5.47 terabytes, still need 862 gigabytes of RAM. For IVF, 5.44 terabytes and 844 gigabytes of RAM. So derived source already gets you halfway-ish, a little bit more than half size of your original deployment. Yeah?
It's multiplied by the number
Yeah, so the replicas are actually multiplied in there, but yes, each replica will reduce in size. Yeah.
Yeah, 4 replicas, that means that if you do derives, then it's going to be 1/4.
Yes. Well, no, not a fourth. It's like 4 times a half, right? Right. I don't know how to say that mathematically. All right, so let's talk about some other methods. So OpenSearch has various ways of quantizing, or there are various other ways of quantizing that reduce the bit count of the vectors themselves.
Wait, let's go back to the previous slide.
Yeah.
So you're essentially storing the source once instead of multiple times.
Correct.
And storing pointers to it. So what happened to resilience?
No, it's the same resilience. Like, storing it twice within the same Lucene index doesn't buy you any resilience.
With the same index.
Yeah,
Why were we storing it twice in the first place?
because that's the way it worked. Like, that wasn't a good design. That was just the design. You had it in your source, unless you disabled it, which you could do, and you had it in doc values because we needed it to build graphs.
So this design is for faster retrieval because the way it works is when you read the document, you can put all of its field values at once. That's
Yeah.
how it sources.
Yeah.
But with vectors, who the hell wants to
Yeah, you don't need your vector retrieved, mostly. Sometimes you might want it, but actually leaving it in source is not a great idea. But in either case, with this file, you can reconstruct the source. And so if a query requests source, you can actually pull it out.
Is that by using like a structure detail and another button?
We have reached the end of my knowledge. I'm not sure how the implementation exactly works, but yeah, I'm not sure the actual structure of the file. But I do know that there's only one file and it actually stores the vectors at full precision. Sorry? So in terms of resilience, right, all of the normal kind of ways that you do resilience with OpenSearch still apply, right? So if this node goes, this .vec file is just the same as any of the other Lucene files that are sitting on the file system. It's not different. It's on the file system, yeah. Yeah. So again, they're on the, like with all shards, I don't want to back up all the way there. So with all shards, you have, at the core is Lucene, right? Lucene reads and writes search indexes. And Lucene itself is a 30 or so file system which memory maps those files for faster use, right? So, and plus you have to cross that with, you have multiple segments, but we don't have to get into that. So in the file system, you have all of the Lucene structures and all of the everything, including this .vec file. This is not different, it's part of the Lucene, yeah, it's part of the shard, put it that way. And so for resilience, a replica is the usual way, right? Okay, so derived source, cool. The next idea is to say, okay, well, a lot of this storage is being driven by the high bit count of the floating point numbers, so can we reduce that? There are a number of different ways to do that. So the first of those is externally, you can create vectors that have lower bit counts, right? Or you can actually apply bit reduction techniques like thresholding is the simplest one to turn a 32-bit floating point number into an 8-bit integer. When you do that, you either have, so binary is a 1-bit per dimension vector that many models can produce, or again, you can threshold and you can do it that way. That means that I get my dimensions divided by 8, right? Because I no longer have 4 bytes per dimensions, I actually have 1 bit per dimension, right? So the total number of bytes there is divide the number of dimensions by 8. Everybody got that? With 8-bit integers, then instead of 4 bytes, I have 1 byte per dimension, so the number of bytes is the number of dimensions times 1. My vectors then, for binary, the storage is 125 million times 1536 dimensions divided by 8. because bytes, it's 1 bit per dimension, so I divide by 8 to get the number of bytes. Okay? Means 24 gigabytes of storage. For the graphs, I use the same formula, but again, instead of dimensions times 4, I now have dimensions divided by 8 for the same reason. And then plus 8 times 16 times 125 million. The graphs then are 44 gigabyte. So that gives me 345 gig of metadata, 24 gig of vector, and 44 gig of RAM, or of graphs. That gives me 826 gig on disk and 44 gig of RAM. Way better. You do lose some precision. You do lose some accuracy here. Turns out binary vectors are actually pretty good. You get in the 90% range compared with exact. Okay? We're only talking about the vector query and retrieval. So re-ranking is a different step, and that's got its own resource needs. Okay, so hold that question. Similarly, for 8-bit integers, we end up with 1.5 terabytes of disk and about 208 gigabytes of RAM.
So you said 90% of accuracy when you're using binary. Isn't it like on disk mode?
Not yet. So this is, again, I'm sending in externally, I'm creating these reduced bit vectors, and I'm sending them into OpenSearch. And then I'm doing, well, HNSW only in this slide for approximate, and then exact would be just without the graphs, right? Yeah.
What was the accuracy with the
Well, approximate or, let me come back to that one too. All right. Now, we also have quantization methods that OpenSearch can employ. In particular, this is the FP16 for the face engine. This reduces to 2 bytes per dimension. Okay, but they're floating point, but they're 2 bytes. When we do that, our on disk is going to be dimensions times 2 bytes per dimension. Our vectors then are, we're going to have 125 million times 1536 times 2 plus 125 million. Because we have the .vec file, we also have a .face file. So we have to actually do these twice, ending with 750 gig. The graphs, again, 440 gig. I won't go through the formula. D times 2 instead of D times 4 or D divided by 8. That gives me 440 gigabytes. So we end with 3 terabytes of disk and 440 gig of RAM. No. What happened? This one or the one before? This one, okay.
Wasn't the purpose of having an all these .vec files so you don't have to do it twice? If you have to do it twice,
Yes. Yes. So we have to take that up with the engineering team. I'm not sure why we need a separate .face file, but we do. Yeah.
What does TS mean?
I didn't hear.
Sorry, what does TS mean?
FAISS?
Or the TS?
I'm not sure where you're pointing.
Engine, the word.
Oh, yeah, FACE is Facebook AI Similarity Search. It's an engine developed by Facebook that's an open source engine that provides nearest neighbor matching. Yeah. Okay, so let's talk disk optimized. With disk optimized vector search, we take our original vectors, which are 32-bit floats. We apply product quantization, byte vector quantization, binary, different compression techniques to create compressed vectors that we use to build the HNSW graphs, right? So when we query, we first query against the compressed vectors, and then we oversample the neighborhood and then rescore based on the full precision vectors that we retrieve from disk. So on disk, again, preserves a lot of the accuracy, but reduces the RAM need by reducing the bit count of the vectors in the graphs. Okay? So, and all of these, by the way, ever since I said derived source, I've been including derived source in all of these calculations, including this one. That's the includes derived source, right? So the on-disk mode supports compression levels that let you set everything from 1 bit per dimension, or 32x compression, down to full precision 1x compression. In this case, we're looking at 32x compression. We're taking the graphs we're creating are with binary vectors, and the on-disk is the full precision vectors. So we have our full precision vectors that we're still storing in the .vec file. We have the graphs that are now 44 gig instead of 860 gig. And that gives us 1.6 terabytes of disk and 44 gig of RAM. I am going to go somewhat quickly through this. So along with all of these approximate methods, and you can see like the strategies of reducing bits, another strategy is instead of reducing bits by thresholding or by truncating or doing any of that, well, what if instead we find centroids for subvectors of various, or a configurable length, and then use those centroids as a way to find nearest neighbors using centroids of the query graph. So compare the query graph to all of our centroids, and then that gives us the match. So what we do is we take our, in this case, 1024-bit vectors, we split into m subvectors, 8 for instance, and then we use k-means, again, clustering, to get 256 centroids for the subvectors. We then code those up and use 1 byte to store them in a table so that we do the retrieval, we also find the centroids and the subvectors, and we just look it up as a coded subvector. In this case, you have a very high ability to reduce the bit count, to reduce the latency, but you lose a lot of accuracy at the very compressed level. So in this case, we have 125 million vectors. This is our formula, m times code size divided by 8. That gives me 769 gigabytes of vector storage. And then I have the graph storage that's 17 gig. So with replica and everything, I'm at 1.6 terabytes and 17 gigabytes of RAM. Can be very small, fast, and lossy. Okay, so we talked about a lot of different ways of storing, quantizing, product quantizing your vectors to get various deployment shapes. The full precision exact is what's going to give you the exact matching is 100% accurate at full precision, but the latency is going to suffer there, right? You're going to have greater than a second of latency, certainly at 125 million vectors. A brute force algorithm is really going to be slow. If we use full precision vectors with exact search and derived store, that drops us down in terms of storage. Accuracy remains the same, latency remains the same. Oh, shoot. If we do HNSW with full precision vectors and derived source, we are at 8.5 or 5.47 with derived source, terabytes of storage, 862 gig of RAM. We'll have near perfect matching, probably 99% accuracy, and our latencies will drop to around 50 milliseconds. You guys can read the table, but I think the points to call out are to look at the balance between storage and RAM consumed, accuracy, and latency, right? So disk search in particular, we're looking at up to 200 milliseconds for the initial query against the reduced bit vectors, and then the trip to disk to pull in full precision vectors, and then the rescore, right? So it's a longer latency, but you're getting really good RAM characteristics and really good storage characteristics. Product quantization, anything that's like at the 70% accuracy is kind of unacceptable. So while you can do a lot with product quantization, you have to be really careful to maintain your accuracy, right? But it is the smallest. So that's the trade-off, right? And that's kind of the point of this slide. When we're thinking about vectors, we want to think about the triangle trade-off between cost, latency, and recall. And this is graphically looking at all of the things that we've been talking about. We have exact KNN in the top left corner, top right corner for you guys. That is the largest cost, but is also the most accurate, but also can be the highest latency, versus disk mode, where you have a reasonable latency, a reasonable recall, and the cost is much less. We have our codings in terms of memory optimized, scalar, sparse, we didn't talk about sparse, binary quantization, product quantization, varying on the accuracy and all kind of similar in the latency characteristics. And with some variation in terms of cost, but generally lower in the cost, lower in cost. So let's return to our original problem and just talk a little bit about the rest of the resources in terms of Java heap and CPU. So as I said, the shards themselves are the things that do the work. So the first thing we think about is, okay, well, how is this going to shard? So let's use on disk with 32x compression rate. Our storage for our primary shards, 812 gig. Recommended for ANN workloads. ANN workloads actually favor larger shards. Why is that? Well, because what you've done is you've cut up the search space so that you have small neighborhoods. And so when you're actually querying, you can put more data more densely packed, right? Because you're actually filtering into a small set of it to do the actual search. 50 gig plus. For a search workload for just data, text kind of search workload, we would recommend 10 to 30, right? So 50 plus, maybe as high as 75 gigabytes per shard. But let's say 50 gig. We take our 812 need, divide by 50 to get 17 shards. Whenever you're figuring out your shard to node ratios, always good to do it in multiples of 3. Within AWS, you'll deploy into 3 different availability zones. And so being able to split it out 3 ways is a good thing. Even not within AWS, even on-prem, you should have multiple zones for isolation and resilience. So with the replica, we're looking at 36 total shards. Now, on disk with 32 compression rate again, these 36 shards, as I said, they're going to map to CPUs to do the work. And the general recommendation that we have is to use 1.5 CPUs per shard. Why is that? Well, because if I use 1 CPU per shard, and that shard is 100% occupied, I got no CPU left. And there's lots of other stuff that goes on in your cluster, including segment merges and communication and all kinds of other stuff. So you can't 100% occupy our CPUs. A good target is 2/3, right? 67% with the search workload. That works out to 1.5 CPUs per shard, right? So we're going to target 54 CPUs in this cluster. Then in terms of RAM, we need 44 gig. So we're going to recommend a 75-25 off-heap heap distribution. And we're recommending 32 gig heaps. This is an example, right? How much heap you actually need for your search workload depends a lot on the queries that you're running and how much of the heap is consumed by transient structures that are actually doing lexical search. So if in this case, if we have a heavy use of the attributes for filtering, we would want to go big on the heap. So if we do that and the 75-25 ratio, then we need 120 gig of RAM in this cluster, okay? So I'm just going to pick a data node, and because I'm an AWS solutions architect, I know AWS nodes the best. I'm going to recommend the i4i 2x large. This has 8 vCPUs each, 64 gig of RAM, 1.875 terabyte SSDs, and it includes, because it's an Intel-based instance, OpenSearch will automatically use Intel-based vector acceleration. So in this case, we need 9, And that's mostly based on the need for 54 CPUs and to be able to be divisible by 3 into 3 availability zones. That works out to about $7,000 monthly. QED. So any questions like, yeah?
For the exact score, the exact match or exact storage, there is no RAM. How it works without RAM? Where is the
So that's going to go on the heap. So the question is, okay, with exact matching, how is that not in RAM? One answer to the question is when you use approximate methods, all of that is loaded separately into RAM for fast processing. If you're not using it, then OpenSearch is just going to use the normal caching that happens with the vector files that are sitting on disk. So GPU will help. Actually, no, GPU won't help. No, you don't need GPU.
But what is the disk to memory ratio? How I differentiate?
So that one, there's not a specific disk to RAM ratio that I can say. Yeah. All right, so just a couple of things. OpenSearch obviously brought in rich vector storage and matching. Trade-off, the key trade-off is latency, accuracy, cost, and carefully, I don't know, my slide died. Carefully consider the workload itself and all of the different options. I'm just flogging a couple of things. OpenSearch ML Quick Start is an open source project on GitHub that I'm working on that has examples of all of these different ways of doing vector search. Also, I wrote a book with a couple of other authors. Go ahead and keep an eye out for that. Looks like my time is done. Thanks very much.